Um, well, this is us. We are working several years in the telecom sector. We have more than 10 years in the telecom sector. And David has somehow like 5 years and have been working a lot in IoT, analytics, big data, and so on. And we are going to talk about this tool we developed as a part of this company. Avery is a consultancy firm. I think this is the only consultancy firm that is in the whole event. But we have a characteristic, and it is that we have been working a lot with this telecom sector, and we are part of entity data a company that is part of entity group in Japan. So, what we want to talk about here is one of the biggest challenges that all telecommunication companies are facing nowadays, and that is customer experience. That is the biggest battle that we need or the most important battle that, at least in Latin America, companies are facing in order to gain market, optimize revenues, in order to get all those objective or specific challenges they need to face. So to understand that, and we ask some very quick questions: are customers satisfied? A long time, companies have been working a lot in network performance, but we will see that right now that is not enough. It is not enough to deliver to the customer high throughput, to deliver to the customer data integrity, to deliver to the customer less dropped calls. And actually, how do customers perceive the service? Maybe customer experience is the next battleground. And the challenge has evolved. How has it evolved? In the past, we have problems that were easy or easier, at least, than today to tackle. For example, if a wireline was down or was up, that was enough for the customer to perceive a good or a bad customer perception. But right now, the customer has many different problems because the use of the service is more faced to the apps than actually faced to the infrastructure that the company of the telecommunication company deploys. And actually, everyone in the telecom sector knows how much does a company of this invest in order to attain that customer experience. So, we've been doing a lot of things, even with all these big data technologies, even with Flink, we have worked a lot in delivering analysis, our customer complaints, to understand Net Promoter Score, to understand churn, over technical issues, to understand, of course, network performance, to understand how many or all those business support platforms operate, and how does the customer perceive the perception over all that. But there are new problems, and new problems require new tools. All this information or all these charts that you see here were actually built in using Flink, using Hadoop, using all that, in order to have all the network performance, the whole network. That is like our first data source for the telecom sector. We started by network performance. Network performance has a lot of data, a lot of KPIs. Every equipment has a really big set of KPIs. For example, a cell has, like, I don't know, in 2G, 200 KPIs, in 4G, 300, and so on. So we have a lot of KPIs only over one kind of equipment. And one of the first things that we did was to build a platform that allowed us to analyze all those KPIs and be able to build our own KPIs for the users of the tool to define their own KPIs the way they want it. Because, for example, well, the network has different technologies, different vendors, different sources of data. So it was really important to be able to calculate all those KPIs dynamically. And that's how we started. And that was the challenge at that moment, a long time ago. But we needed to get ready to face this new challenge. So the customer perception, not only the network performance, and not only how the customer, if the customer calls, if the customer tells me that his internet is slow, but to actually try to understand how is the customer perceiving the service via mean opinion scores. So we investigated, we did our research over how main players measure that, how what tools did we have, well, our customer, how what were their capabilities to gather information, and we built mean opinion scores over video streaming, web browsing, and main smartphone apps. And that is calculated real time, real time with enrichment of all that knowledge that we already had. But this information doesn't come from the network. This information comes from the user, the register that the user leaves when they use internet. For example, if the customer navigates in Facebook, to say only an example, we can see that he entered, he navigated, he had some quality or some metrics with which we can measure quality real time. So we calculated those mean opinion scores to hit straight into customer perception, to be able to anticipate customer problems before the network gets degraded. So, and let's be clear that I'm not talking about prediction or machine learning or any of that. We're talking only about, we did our research with data at rest, and we generated or calculated mean opinion scores, defined how to calculate mean opinion scores, and those mean opinion scores are generated automatically with information to do root cause analysis also real time. For example, if a customer has, I don't know, many stalls in the video, if the customer experiences long times on the web page load, if the customer is navigating, I don't know, social media and the photos don't load when they have to, we can see that, and we can per customer, and of course aggregate all that information with Flink. We can calculate that mean opinion score and enrich it, for example, with network KPIs. And that way, I can have a customer that has a degradation of video streaming, but I already know that there is an equipment that is degraded. So that must be, or should be, or might be the root cause for that specific problem. Who are the users? That is more like business side of this presentation. There is a service operations center. Yeah? Those are the guys in chairs like this. They are watching at screens and they are seeing this equipment is degraded, or this device is off, or the customer, I don't know, many things. And this service operations center will monitor these specific KPIs. And they will see how many customers, for example, in the whole country, or in a specific region or in a specific city, if the proportion of customers that have less experience that we expect, that means a mean opinion score lower than we define and than we calibrated, when that number goes up, we have an alarm. And we can see it on the screen, but we can see it also connected to fault management systems and all that David is going to show you in a minute. So it's real-time, end-to-end monitoring of service perception. That is what it is. So what do we do with that? We enhance customer recommendation, reduce churn, all that, all those things that every telecom company wants. But most importantly, what they are using it is to invest better. To know how to help them use better their resources to CAPEX and OPEX. That is what they are using it right now. But of course, in the short term or mid term, they should see also, they can be able, for example, to query a specific customer, what's their customer's perception. And of course, they can aggregate that and see, for example, a corporate customer, or all the lines of a corporate customer, how is a customer perception measured, because the system is dynamic, and we can define those metrics and aggregate them the way we want. So David is going to explain the more technical part of this.
Thank you, Dahyr. Well, really, what Dahyr just said make us remember a bit that really it's a use case not just all about the tools that we have, the trillions of messages that we might be processing, but also a use case is about the processes behind it, what you finally do with the information. But obviously, there is a technical part of it, and we're going a little deeper with that. So why did we choose Flink? Well, really, Flink's not really much known in Latin America. And there are, I think, not many companies in Latin America using it right now. But the complexities of the telecom business really needs this kind of technology, as we're going to see, because we needed all of those things to make that to become in reality. And really, this Apache Spark and Apache Storm has some of those things. For example, has per-event processing, has event time processing. But when we come to the more customized operations, Apache Spark and Apache Storm all fall short. When we need session windowing, multiple window firms, or custom window firms of any kind, and of course, if we need complex event processing, well, there is not a easy way to implement those things in Spark or in Storm. So we really needed a much more capable streaming engine to do that kind of things. And we then started building this architecture. In this architecture, we ingest first this kind of data, the DPI data, the network performance data that Dahyr talked to you about before. And all that information is ingested via Apache Nifi into the Kafka topics. Then all that information is processed in Apache Flink and sent back to Kafka. Then there is another microservices running the complex event processing using some rules. We're going to see that in a few slides. And there are some interfaces with the alerts manager that the telco already had. So we send them all the information, all the alarms that we generate, so the service operation center can then monitor those alerts and make action plans about it. The analytical data store, the time series database, is Druid, and all the visualizations then are attached to that data store using Shiny and Apache Superset. So this architecture uses a lot of components of some pre-existing Hortonworks.platform cluster that the telco already had. And we try to use all of these in the better way, but using Apache Flink at the core of all the processing, which is of course the best there is. So we told in this slide that we had these CSVs and those XMLs, but how big are those sources that we're ingesting? Well, right now we're processing 23 billion records a day, and we're growing really fast because we're planning at the third, maybe fourth quarter of this year to more than duplicate that. We're adding more sources to the mix. We calculate that more or less we're going to have something like 53 billion records by the end of the year. So this is really a lot of data coming in and out from Apache Flink. So we wanted to show you some of the challenges that we've faced during the developing of this solution. The first of this, in the early days, when we were just assessing the capabilities of Flink and really getting to know with Apache Flink, we needed to do this multiple stream enriching. And when you only have one source for enrichment, it's quite straightforward. You just have a main stream, you have some control stream, which is really we're not that big, which would be like the network inventory, network element inventory. And then you do a connect in the code, you do a co-process function, and then you do whatever you have to do afterwards, and that just works, right? But when you have two or more sources for enriching, things get a little more complicated. The thing is that in our case, all those sources for enriching are related among them. So you could also think that you maybe want to filter or join those sources, apply some logic, and then with the filtered data, then do something else. So that's what we did. We had the network inventory and some geographical information. We connect those sources. They both were control sources, were really small data sources. And things got wrong. That didn't work because the data was not flowing all the time. Those were really small, some thousands records in each of them. So that didn't work. So there were some times we didn't know what to do, what this didn't work. But we realized then that what happened is that you really need to keep your stream flowing. And that's what we did. In the second attempt, we had, again, the network element inventory. We had the main stream, which is flowing all the time. And we connect them, process them, and then added the other source, the geographical information, to that string, which always was flowing also. And at the end, we did the filtering. So in that order, that worked. So we learned from the early days of developing this solution that when you're processing, when stream processing, really the order matters and matters a lot, because that's the difference between something that works or something that doesn't work. So in summary, keep the stream flowing, right? And a quick tip here is that we also learned during these early phases that we needed to keep intermediate data objects as flexible as possible. In the second example, we had all the data objects were case classes in Scala, and each step, each enriching step was needed. The, their output was a case class hard coded. That meant then that if you change the order in which you do the enriching, then you need to hard code again different case classes because they are not going to match as before. So then obviously that wasn't really nice. So what we did was to only model as case classes the real entity, the real business entities. And for enriching, we use tuples as intermediate data objects that no one really cares, but in the final step, prior to the sync, then we do a specific data object for that too. But intermediate data objects are needs really to be flexible in order to mess around with the order and not to rebuild the entire data model every time we change the order of things. So a second challenge we had was session windowing. When we were designing this part of the solution, we thought this surely is really difficult to do because in Spark or in Storm, which we had some knowledge of, was really difficult to do. But really, the solution in Flink was much easier. So we had this problem because we needed to define a session or some grouping for the experience of users. So if you have a cell phone and you're looking at a web page, the DPI data has all the requests that your browser did, which maybe are hundreds of requests of images, CSS, style sheets, JavaScripts, and so on. But we really don't assign a experience to all of those tiny requests because you as the end user of telecommunication services, you don't really care if a single image don't load or if a CSS is loading or not. What you really care about is if the web page loads and you can read their content, right? So we aggregate all of those requests, all of those records in one only session that then we assign a score and see if the experience of that specific page of each specific user is good or not. So really, we wanted only to show you this because we found that with Flink, it was really simple to do this. So simple because the API provided by this amazing community is built to do that really easy. But the challenges don't end here. We now had to do some custom window firings, and we are going to talk a little about that. because we had this problem. We had hundreds of different formulas that we needed to calculate, because as Dahyr talked you about, each tiny element of the telecom network has a lot of counters and data, but we need some calculations in order to extract value from that data. So we need to compute these formulas we already have defined by an hourly basis, because all of this data comes each hour from each and every element of the network. So this was our first solution. We created a consumer of the Kafka topic, and because of the nature of this data, there are many of this data that comes late. So we then assigned a bounded out of orderness timestamp structure in order to wait for that later data and have then the watermark a little behind to allow the data to catch up. So the thing is, we have this example. We have a timeline with processing time. And let's say that some of these information came at 9 with information of 8, right, an hour before. That means that the watermark is 1 hour more behind, because we, in the bounded out of orderness structure, said that it was a time of 60 minutes, right? So our watermark is at 7 a.m. There is more data coming at 9:10, and more data coming. And finally, at 10 a.m. Comes the first data of the previous hour, 9 a.m. And then the watermark gets to 8 a.m. And finally, the window triggers and does its calculation. But how much time we have to wait? We have to wait to finally have this result. We have all the data. We had all the data since 9:15, and we have to wait all the way to 10 a.m. to finally have the result. So that is too much latency added not by Flink or by any processing, but with our business logic that was a bit flawed. So we then have a second chance to do things better and to solve these kind of problems, new problems that we had then. So this clearly was not the best way of do things, as we had problems if the data come early or if time come later than we thought. In both cases, we were not going to have a good result, and we were going to have too much latency. So we had a new solution coming up. And for this time, we were not using event time. We were using now processing time. And we're now going to see why. Now again, we have a timeline for processing time. And again, the data is starting to coming up. And the thing is that now we define a time window that is for 1 day. It's a really long time window. And we have then a custom trigger that is a continuous processing time trigger, which every 10 minutes does a triggering of the window. And that means that at 9:10, because the first information came at 9, then 10 minutes later, we have our first triggering, right? But in this time, we didn't have all the components needed to to do the calculation. So at this point, the first firing just returned known. There was no result. But then data continued to flow, and 10 minutes later at 9:20, we again had this continuous processing time trigger, and again tries to do the calculation. And in this time, in the second firing, we are having our our result. So we only had to wait 5 minutes for the data, which is obviously much better. And the processing, well, continues. So in this way, using a custom trigger, a time window, and using also a custom evictor for eliminating the data that already was processed, then we achieve a much better latency, we achieve a much better scalability. But of course, at the cost, we have now more CPU cycles involved. We have to, each 10 minutes, check if we have all the data needed to trigger the calculation or not. And we have a much bigger state, but anyway, under control. And the last challenge, which is a really recent challenge we were facing, is about CEP. We needed to run several complex event processing with different patterns on different data sources. So we clearly couldn't do this hard-coded. That really is not an option for us. Because there are always new rules added, modified thresholds, and so on. So our solution is to make it dynamic, more or less dynamic. We were going to see why. We use JSONs to configure the patterns needed to trigger the complex event processing. And then at the start of the Flink job, the Flink processes parses those JSONs and start running all of the topology involved. So this is an example of how those JSONs look like. We have some variables for the processes. And the interesting part is the patterns array that we have at the end that defines each of the patterns that conforms the complex event. So this pattern has two little patterns inside. The first one has a condition that the score has to be between 3 and 3.5. That we need one of more of those. That's the quantifier, the plus in there. And the end pattern is that if the score after one of those one of those conditions between the score between 3 and 3.5, if the score falls even more less than 3, then if this happens within 10 minutes, then the complex event is triggered and an alarm goes to the alarm manager of the telco, and someone does something about that. The thing about this is that right now, for any change in this JSON to take effect, the job needs to be restarted. This is more or less acceptable right now. We're only doing some of those steps. It's a recent development right now, but of course we would like to make this on the fly, to do this with no downtime whatsoever. So that would be nice, but as of now, as our understanding, there is no way to do this in Flink because the topologies are fixed right now, and maybe that changes in the future. In that case, of course, we will using that in our advantage. So that's mainly the challenges we've been facing, but the path doesn't end here. So we're going to add more sources really soon. We're going to try the ML, the machine learning library, to enhance our anomaly detection capabilities. There is a data science and machine learning area at Everest, and we're working with them to do these kind of things. So there is a lot of good things that are coming for this project. So this is basically what we had to show you. Thank you very much, and I don't know if you have any questions. Okay.
Hello. You mentioned in one of the slides that you have to keep stream flowing. And can you explain one more time, maybe what's the science behind that? Why the stream should be flowing? And you're connecting to streams. I guess one stream is flowing all the time. Like every second you have a new message, and in another stream you have messages every 5 minutes, for example, right? So what's the challenge here?
Okay, the challenge was that we were using control data sources if they were real streams that are always flowing, but those streams were not flowing because they were only a really small data set we use for controls, we use for loading some business logic. So if you have those, two of those connected, and they only come like a day, they only come once a day, then you're not going to have any data flowing to the downstream operators in that whole day, because the flow is not uniform. So we needed them to do this enriching one at a time, because we had this real stream, the main stream that was in green in the slide. This stream is flowing all the time, 5 minutes or so. There is a new record always. So if you do that one at a time, then you keep then the stream flowing. That's what we meant.
Okay, I have another question actually. So you also mentioned this JSON configuration file. And what is the challenge to reread this every several minutes or every time it changes? You mentioned that it's not possible in Flink. And what are the challenges you're facing?
Well, the thing is that we can reread anytime you want, but then you can't close or delete or remove the existing CEP that are currently running to then upload the next parents that are uploaded from the change file. So the challenge is not about just reading a file or not, but what do you do with the old complex events that are now processing? There is actually no way to close that or remove that current processing and then put the new ones. There is no way to do that now.
Got it. Thank you.
Okay.
Another question?
I was curious about how you calculate the mean opinion score for video services, application, smartphone apps, web browsing, etc.
Okay, we have all the registers, the data registers, and we can know specifically for a customer, of course, anonymize the customer. We cannot know a specific person, all of that. But we can know for a specific session, there is a set of registers that we can get, that the company has. And with that, we can know, for example, there are algorithms that are applied over that information to calculate, for example, video stalls. And to calculate, for example, a downshift in the resolution, upshift in the resolution. There are many metrics that we calibrated via surveys and via studies and via best practices in the market, and we developed our own mean opinion score. So we can know, for example, if the customer, even for example, just to note a simple example, if a customer has an upshift, it is also penalized, even if it is an upshift. We found that the customer doesn't like the video to move. They want to have it in a good resolution and keep in the good resolution. That is only one example, of course. But for example, for video, that is the way. Any video from any provider, Netflix, YouTube, anyone. Any other question?
Then thank you very much, guys.
Thank you.
For the talk. Round of applause.
Thanks.